For a function to be continuous on a closed interval, AB, it has to be first continuous on the open interval, AB. So if we've got our function, and there's A, and there's B, I'm going to draw a portion of the graph like that. This pretty much has to happen, and this is the graph that we would have if we say the function is continuous on the open interval AB and has hope of being continuous on the closed interval. Because by drawing the graph where it's actually approaching a particular point, rather than having a vertical asymptote, rather than being some kind of crazy oscillating infinitely often behavior, the limit, because it's behaving well there, the limit of f of x as x approaches a from the right equals, well, it exists, and we need it to equal f of a. Now, I don't have an f of a on here, so if I want this to have hope of being continuous on the closed interval, I don't want the dot here, I don't want the dot here. I want it to be what that value of the limit is going to be, f of a. So erase that one, erase that one. I want to fill in the dot if this is going to be continuous on an interval that includes that a as the endpoint. Likewise, this limit of f of x as x approaches b from the left exists because as x gets close to b from the left, we're approaching a point. And now we want the function to be defined to be, whoops, missed it. Oh, that was unfortunate. Come on. Wow. Am I going to miss it again? Maybe. F of b. We want it to be defined to equal f of b. So basically we need a solid dot at A, and the graph needs to be approaching that solid dot. We need a solid dot at B, and the graph needs to be approaching that solid dot. And then we can say the function is continuous on the closed interval, including both endpoints A and B. Now, there are situations where it might look like this. And then what we would say, there's A, there's B, F is continuous on this half-open interval. We can include the A because it's approaching the dot, the solid dot at A, but at B, it's approaching the wrong dot. It's approaching the open circle instead of the solid dot, so we cannot include the B in the interval where it's continuous. So we could do it, and we could put the open circle at A if we wanted to, and the solid dot at B, and include the B and not the A. Here's kind of an important point that I need to bring out here. Suppose that we have a function, and there's A right there, and it's doing this, and then it's doing this, and let's say it's doing this, and we've got B over here. Can we say the function f is continuous on the closed interval AB? No. Well, here's the thing. When I guess I'd taken this course many years past, and I started teaching the course, it seemed like a contradiction because you can look at it and see it's not continuous at A, is it? Right? It's not continuous at A. There's a jump right at A. But here's the thing. In order to be continuous on a closed interval that contains A as a left-hand endpoint, it doesn't have to be continuous at A. It just has to be continuous from the right at A. That's